So in the previous module, I was talking about HMO approximation, and I have given you one example of a ethylene molecule also. So just a quick recap: in HMO approximation, what we do, we suppose the molecule to be all the sigma bonds to be frozen, and the only pi electrons moving in the field created by the nucleus and the sigma electrons. So this was the first approximation given by Haeckel. Okay. So and the second one is, I said you that when you have the conjugated diene molecules or conjugated molecules in organic chemistry, then for each of the carbon atoms you have one pz orbital, and these pz functions are taken as linear combination of these pz orbitals wave functions is taken as a trial function, and then variation treatment gives you an n by n determinant. Okay. So this and once you write the variation the determinants, then there is an approximation for H11, H22, H33 and H44, all which is Coulomb integral, and I said you they are represented as alpha, and then all S22, S33, S44 means Sii or Sjj is equal to 1, okay, and all Sij is equal to 0, and all H12, H31, H41, H32 means, but in the subscript is not same. These are called resonance integral or exchange integral. They are given a symbol beta, provided that the number which is given in the subscript are closest neighbor. Means if we are talking about H12 and 1 and 2 are bonded by sigma bond, then it will give in a beta symbol. If it is written H13 and 1 and 3 is not directly bonded by sigma bond, not nearest neighbor, then it will be given a 0 symbol. So this was the approximation. This we applied to the ethylene molecule, and we found two different eigenvalues, two different wave functions, and we found how the what is the electron density present on each carbon atom, what is the charge density present on each carbon atom, and what is the bond order between C1 and C2. So this was the topic of the previous module. Now the same thing we are going to do, but for a different system in allyl system, where you have 3 pi electrons. So naturally, if you have an allyl systems where C1, C2 and C3, and each of these you have a pz orbital, then if you treat psi mo, how will you write psi mo? Psi mo will be summation of C1 phi 1 plus C2 phi 2 plus C3 phi 3. So it will give you a 3 by 3 determinant, because you are using phi 1, phi 2 and phi 3, where each of these phi 1 and phi 2, phi 3 represents one of the pz orbital present on carbon number 1, carbon number 2 and carbon number 3. Okay. So this we can write. Now, I said you, if you are writing this and you have any confusion, you just look at the diagonal terms. This is diagonal term, this is diagonal term, this is diagonal term. Sorry. This is diagonal term. Okay. So all this should have the same coefficients, same number in the subscript H11, S11, H22, S22, S33, S33. So this will give you the right kind of determinant which you have to write. Okay. Now if you using HMO approximation, what you can write? You can convert this into alpha and beta form. So the first term will be alpha minus E, because H11 and S11 will be equal to 1. So H1 alpha minus E. H12 both are directly bonded, so beta term. H13 is not directly bonded, and S13 has to be equal to 0. So just look at this one. This is alpha, this is equal to 1. H12 is what? H12 will be beta, because 1 and 2 are directly bonded. And what will be S12? S12 will be 0. So ES12 will be 0. H13 will be 0, because they are not directly bonded, and S13 will also be 0, because it is the because of the orthogonality of phi 1 and phi 3. This is 0 because of the orthogonality of phi 1 and phi 2, and this is normalization of phi 1 and phi 1. So it is 1. Okay. So this way you can write alpha minus E, beta is equal to 0, beta and 0 are the 3 terms in the first row. In the second row if you come, H21, again 2, 1 are nearest neighbor, so it will be beta, and H22 minus ES22 will be alpha minus E, and then H23, now 2, 3 is also directly bonded, 2 and 3 is also directly bonded, so this will also be beta. Okay, this is what you have to do it very appropriately. Otherwise, if you make mistake here, then every calculation will be wrong. All calculations will go wrong. Okay. Now H31, again 3 and 1 are not directly bonded by sigma bond, so it will be 0. H32 will be beta because S32 will be equal to 1, will be equal to 0. So you will have beta only, and H33 again it will be alpha minus E. And as what we did previously, we divided each term by beta, and we said that alpha minus E divided by beta is equal to x. So if you do that, alpha minus E divided by beta is equal to x, and you divide each term by beta. So the first term will be alpha minus E divided by beta, so it will be x, and then you divide beta by beta, it will be 1. This is 0, so this will remain 0. Then again you divide beta by beta, it will be 1. Again you divide alpha minus E divided by beta, it will be x. Again you divide beta by beta, it will be 1. Now look at this one, 0, so it will be 0. Beta by beta will be equal to 1, and the last term alpha minus E divided by beta will be x. So both these determinants you must write appropriately, and then only you go for calculation. You see here all the terms on the diagonal of the matrix is same, alpha minus E, alpha minus E, alpha minus E. This you should get, x, x and x, all terms are same in the diagonal. So if you are getting this, then your determinant is fine. Okay. Now once you have the secular determinant written, then what do you find out? From this you find out the value of x. Okay, and see how many values of x you get. How do you write this? The value of this determinant? Take the first term of the determinant x and then look for neglect the first row and first column, because you have already taken one term from this one, and then consider the 2 by 2 determinant like this one, and this is what, x square minus 1. So x into x square minus 1, then take the second term and neglect this column, middle column, because the first term of the second row of the first row, second term of the first row you are taking. So first row and middle column will be neglected, and rest 2 by 2 determinant you will consider. So it will be x into 1, x minus 0. So it will be x minus 0. This is equal to 0. Okay, and then the third term is 0. So if you multiply by 0 to this 2 by 2 determinant, it will be 0. So third term we are not right. I have not written. Okay, and if you solve this one, what you get? X cube minus 2x is equal to 0. Okay, and if it is x cube minus 2x is equal to 0, then what you can write is x into x square minus 2 is equal to 0. Now this equation will be satisfied when x is equal to 0 or x is equal to plus minus root 2. If x is equal to 0, it will be satisfied, and if x square minus 2 is 0, then x square will be, if x square minus 2 is 0, then x square is 2. So x is equal to plus minus root 2. So you have this one. So you have three different values, x is equal to 0, x is equal to plus minus root 2. Okay. Now if you use this x value and you write the energy equation, energy equation you can write, because alpha minus beta E is equal to, sorry for my poor handwriting, but just alpha minus E, alpha minus E beta x, and what you can write, alpha minus beta x is equal to E. So just put the value of x here into alpha minus beta x and you will get the energy. And what was the value of x? X value was 0. in one case. So, energy will be alpha only, and in another case it will be alpha plus root 2 beta or alpha minus root 2 beta. So, that is what is it, alpha plus root 2 beta, alpha is equal E2 is equal to alpha because x is equal to 0, and E3 is equal to alpha minus root 2 beta if x is equal to plus root 2. Now, again you can calculate and you can see which is bonding molecular orbital, because alpha and beta both are negative. So, naturally the first one is even alpha plus root 2 beta with the bonding molecular orbital, and E3 alpha minus root 2 beta will be the anti-bonding molecular orbital, and in between you have a non-bonding molecular orbital. Okay. So, if you draw the energy levels, these are the energy levels for bonding molecular orbital alpha plus root 2 beta, for non-bonding alpha, for anti-bonding alpha minus root 2 beta. And now I have given 2 electrons and we say this to be allyl carbocation. If you have 3 electrons, then it will be allyl carbon free radicals, and naturally the third electron will go to the non-bonding molecular orbital. And if you have 4 electrons, then it will be allyl carbon ion, and fourth electron will also go into the non-bonding molecular orbital. So, for each of these allyl carbocation, allyl carbon free radical and allyl carbon ion, one can find out the pi bond energy. So, if you look at this one, allyl carbocation, what do you have? Alpha plus root 2 beta. So, alpha plus root 2 beta is multiplied by 2 because 2 electrons you have, this is the number of electron. And this is the bonding molecular orbital energy, and if these electrons are free, then it is 2 root 2 beta. Okay. What will happen with carbon free radical? Okay. You have 2 electrons in the bonding molecular orbital and 1 electron in the anti-bonding molecular orbital, and here you have one number, if you want you can write 1 electron, 1 multiplied by alpha will be alpha, so I have written alpha only. Okay. And if the 3 electrons are free, then minus 3 alpha. So, as compared to free electrons, what is happening to the energy of when they get bonded, that we are seeing. Okay. So, E pi will be equal to again 2 root 2 beta. If you have 4 electrons, then 2 electrons in the bonding molecular orbital and 2 electrons in the non-bonding molecular orbital. So, plus 2 alpha and minus 4 alpha when they are free. So, it is again 2 root 2 beta. Okay. So, what you find here, E pi energy for allyl carbocation, allyl carbon free radical and allyl carbon ion are same to root 2 beta. Okay. In contrast to this, for a localized allyl system consisting of one ethylenic bond only, in all case we will have energy equal to 2 beta. So, you see, if you have an allyl system C double bond C like this one, and you have restricted this to this one ethylenic bond, then the energy was only 2 beta. Okay. If you have one ethylenic bond only even in this one, this is your allyl system. Okay. But if you have this one, a delocalized system where this electron is localized on the 3 carbon atom, these 2 electrons are localized on, instead of being restricted to the 2 carbon atom, they are delocalized to the 3 carbon atoms. What you get energy is 2 root 2 beta. Okay. So, the delocalization will improve the energy by 2 root 2 beta minus 2 beta. So, it will be around 0.2828 beta. Okay. Got this one? What I want to say? We have just calculated for the ethylene molecule E pi. What was the energy? Alpha plus beta, and 2 electrons you were having here. So, you said that for these 2 electrons, 2 into alpha plus beta minus 2 alpha has given you 2 beta. So, if the bond, if the pi electrons, 2 pi electrons are localized on the 2 carbon atom, the E pi energy which you get is 2 beta. If the same 2 pi electron you make it delocalized over 3 carbon atoms in a chain, which is in the allyl system, then the energy which you get is 2 root 2 beta. So, this delocalization leads to more stabilization of the system, and you get an energy which is equivalent to 0.828 beta. Okay. So, this is a negative quantity. So, compared to localized system, these are more stable system obviously, because the now the system is delocalized, or delocalization leads to a stabilization, that you know. Okay. So, see, the results which we are getting from HMO is exactly the same which we should have obtained and which we are aware of, which we are already aware of. Okay. So, once we have this one, the second thing is the finding out the, once we are done with the energy values of bonding, non-bonding and anti-bonding, the second thing is finding out the eigenvalues and eigenfunctions. And what are the eigenfunctions? You started with psi mo is equal to A1 phi 1 plus A2 phi 2 plus A3 phi 3. So, the next task is finding out the coefficients A1, A2 and A3. So, again from the determinant you will add the equation, so simultaneous equations will be written. And so, first row you have 3 terms x, 1 and 0. So, the first row will give you an equation A1x plus A2 is equal to 0. A3 term will not be there because the third term is 0. Okay. In the second row you have 1x1. So, the equation will be A1 plus A2x plus A3 is equal to 0 obviously. Then in the third row you are starting with 0, 1 and x. So, what do you have? You have only 2 terms A2 and A3. So, it will be A2 plus A3x is equal to 0. So, 3 simultaneous equations you obtain from this determinant is this one, A1x plus A2 is equal to 0, A1 plus A2x plus A3 is equal to 0 and A2 plus A3 is equal to 0. From these equations you have to find out the value of A1, A2 and A3. Okay. So, now x we already have x is equal to minus root 2 for the bonding molecular orbital. So, use this value minus root 2 and use the first equation A1x plus A2 is equal to 0. So, what do you get? A2 is equal to root 2 A1 you can write. Then use the third equation A2 plus A3x is equal to 0, and what does it mean? It means that A2 is equal to root 2 A3, and if you look at these two equations, A2 is equal to root 2 A1 and A2 is equal to root 2 A3, what does it mean? A1 and A3 are equal. So, we conclude that A1 and A3 are equal. Again, from normalization condition, what do you get? This you will get exactly in the same way as you got for ethylene molecule in the previous module. So, here also you can get A1 square plus A2 square plus A3 square is equal to 1. And if you want, you can do again, write the normalization condition, which will be A1 phi 1 plus A2 phi 2 plus A3 phi 3 multiplied by again A1 phi 1 plus A2 phi 2 plus A3 phi 3 d tau is equal to 1, and you will see that all cross term will become 0 and all similar terms where A1 phi 1 you multiply with A1 phi 1 will be A1 square integral of phi 1 d tau and A2 square integral of phi 2 d tau plus A3 square integral of phi 3 d tau, and these will be equal to 1 because they represent the normalization condition. Okay. So, only A1 square, A2 square and A3 will remain. A1 A3, A2 A3 will not be considered, because if it is A1 A3, the phi 1 phi 3 integral will be equal to 0. Okay. So, phi 1 phi 3 integral so that term will not be considered, and you have A1 square plus A2 square plus A3 square is equal to 1. Okay. So, if you use this one and A1 and A3 are equal, so you can write 2A1 square is equal to A2 plus A2 square is equal to 1. So, what you can write 2A1 square root and this A2 you know, A2 value is root 2 A1. So, root 2 A1 value A2 value I have put here, and then what you get, A1 is equal to 1 by 2 and this is equal to A3k. So, it will be what, 2A1 square and plus a square of this one will be again 2a1 square. So, it will be 4a1 square is equal to 1. So, a1 square will be 1 by 4 and a1 will be 1 by 2, and so a3 will also be 1 by 2. Okay. So, if a3, a1 and a1 is equal to 1 by 2, a3 is equal to 1 by 2, what will be a2? a2 is root 2 into a1, so it will be root 2 divided by 2. Okay. This we can write. So, we have a1 value, you have a2 value and you have a3 value for the bonding molecular orbital. So, you can write the function for the bonding molecular orbital, eigenfunction you can write. And what will be the eigenfunction? Eigenfunction will be 1 by 2 psi pz1 plus root 2 by 2 psi pz2 plus 1 by 2 psi pz3. Okay. So, this is for the bonding molecular orbital, because x value I have taken as minus root 2. Okay. If you take x is equal to 0, then you can write eigenfunction of non-bonding molecular orbital, provided you know a1, a2 and a3 values, and the equation remains same. So, for x is equal to 0, non-bonding molecular orbitals, what we can do? We can again find out the a1, a2 and a3 value, and we can write the wave functions. Okay. Now, the three simultaneous equations which we have written earlier, we will be using. The first equation was a1x plus a2 is equal to 0. So, a2 is equal to 0 we can write. Okay. Since x is equal to 0, so a2 is equal to 0 we can write. Then the second equation was a1 plus a2x plus a3 is equal to 0. Okay. So, what we can write? X is equal to 0. So, a1 plus a3 is 0. That's fine. Means a1 is equal to minus a3. a1 is equal to minus a3. Got this one? Then from the normalization condition, what we can write? a1 square plus a2 square plus a3 square is equal to 0. Now, since a2 is equal to 0, so I have omitted that. Now, it is a1 square plus a3 square is equal to 1. Okay. And a1 is equal to 1 by root 2 and a3 is equal to 1 by root 2, minus 1 by root 2. Okay. So, a1 is equal to minus a3. What does it mean? a1 is equal to minus a3 means what you can write is a1 square and plus a1 square plus a1 square is equal to 1. So, because a3 is same, and if you square it, then negative will become positive. So, you have 2 a1 square is equal to 1 and a1 square is equal to 1 by root 2. a1 square is equal to 1 by 2 actually, 1 by 2 and a1 will be 1 by root 2. And if a1 is 1 by root 2, then a3 is equal to 1 minus 1 by root 2. So, you have the coefficients a1, a3 and a2 is equal to 0. So, now the wave functions you can write. Wave function is same. The only coefficient is changing. So, for the non-bonding molecular orbital, psi 2 you can write as 1 by root 2 psi pz1 minus 1 by root 2 psi pz3. We do not have psi pz2 contribution here, because a2 coefficients of the psi pz2 is equal to 0. So, for x is equal to 0, we have written the wave functions. Now, what we can write? We can write the wave function for anti-bonding molecular orbital x is equal to plus root 2, anti-bonding molecular orbital. Again, you will find out a1, a2 and a3 for writing the eigenfunction for anti-bonding molecular orbitals. So, you will use the first equation a1x plus a2 is equal to 0. So, x is equal to plus root 2. So, you can write a2 is equal to minus root 2 a1. That's very easy. Then the second equation is a1 plus a2x plus a3 is equal to 0. So, what you can write? a2 plus a3x is equal to 0. That's the third equation I have written. Okay. And so, from the third equation what you get? a2 is equal to minus root 2 a3, and from these two equations what do you get? From these two equations you get a1 is equal to a3. okay, because A2 is equal to minus root 2 A1 and A2 is equal to minus root 2 A3. So, A1 is equal to A3, and if A1 is equal to A3, then what you can write? Normalization condition, A1 square plus A2 square plus A3 square is equal to 1. Then 2A1 square plus A2 square we can write, A1 and A3 are equal. So, 2A1 square plus A2 square is equal to 1, and so A2 is equal to, and A2 you can write as minus root 2 A1. So, it will again 2A1 square, okay. It will be 4A1 square. So, A1 will be 1 by 2, okay, because it's 4A1 square. So, this is equal to, this is equal to, sorry, from this you get 4A1 square is equal to 1. So, A1 is equal to 1 by 2, and if A1 is 1 by 2, A3 is also 1 by 2, and A2 value you already have, okay, minus root 2, and put the value of A1 is 1 by 2, so it will be A2 is equal to 1 by root 2. So, all three coefficients we determine A1, A3 and A2. Now, we can write the eigenfunction for this system also, for this anti-bonding molecular orbital also. And the eigenfunction for the anti-bonding molecular orbital will be 1 by 2 psi pz1 minus root 2 by 2 psi pz2 plus 1 by 2 root psi pz3. Okay. So, we have the three eigenvalues. We saw the energy values, how does the energy is written for the bonding molecular orbital and non-bonding molecular orbital, anti-bonding molecular orbital, and how the stabilization takes place because of the resonance over 3 carbon atoms of the 2 electrons, that also we saw. And then we find the coefficients of A1, A2 and A3 for all the 3 orbitals, bonding, non-bonding and anti-bonding molecular orbitals. Okay. So, we have these three eigenfunctions psi 1, psi 2 and psi 3 for bonding, non-bonding and anti-bonding molecular orbitals. Okay. Once we have this, what we can do? We can again go and find out the electron density and charge density and bond order and all those things. Okay. But we will be doing this in the next module, because this module will be more longer. In the next module, we will finish this allyl system, and then we will go for a cyclic system. That is, cyclic system will be with the 3 carbon atoms will be cyclopropynyl system. So, in the next module, I will take up that example, cyclopropynyl example. Okay. Thank you for that.